Hello everyone, my group will be working on the APU of the aircraft, the Auxiliary Power Unit. APU is a unit on the aircraft that provides energy for functions other than propulsion. Function will be to run the electrical system of the aircraft. The APU produces 115 volts at 400 Hz as compared to 230 volts 50 to 60 Hz in main power supply. The APU, also a gas turbine engine, not only produces electrical power supply, but it is also capable of producing pneumatic services for the aircraft on the ground and in the air. Besides that, it also allows the aircraft to be self-sufficient on the ground without the need of any ground power supply. The APU is installed in the tail of the aircraft. It is located inside a firewall compartment which has firewall proof. This firewall proof isolates the APU from the aircraft fuselage and the horizontal stabilizers. In any case of fire emergencies where the APU might burst into flames and fire, it will not have adverse effect on the other parts of the aircraft. With so many functions of the APU in the aircraft, there is no doubt that this is a very strong, a very powerful, and an irreplaceable unit in the aircraft. However, we still have to understand what is actually the main purpose of the aircraft APU inside that allows the aircraft to be flying in the air. Without the APU, starting the engine won't be possible. So, the primary purpose of an aircraft APU is to provide enough power for the main engines to start up. Turbine engines must be accelerated to a high rotational speed in order to provide sufficient air compression for self-sustaining operation. Smaller jet engines are usually started by an electric motor, while larger engines are usually started by an air turbine motor. Before engines are to be turned, the APU is started, generally by a battery or hydraulic accumulator. Once the APU is running, it provides power, which are the electric, pneumatic, or hydraulic power, depending on the design and the type of APU that is needed. So all these will start the aircraft's main engines. APUs are also used to run accessories while the engines are shut down. This allows the cabin to be comfortable while the passengers are boarding before the aircraft's engines are started. Electrical power is used to run systems for pre-flight checks. Some APUs are also connected to a hydraulic pump, allowing crews to operate hydraulic equipment such as flight controls and flaps prior to engine start. This function can also be used on some aircraft as a backup in flight in case of any engine or hydraulic failure. There are basically three main sections of an APU. First, the power section is the gas turbine section of the APU that produces the power. Secondly, the low compressor section is a shaft-mounted compressor that provides pneumatic power to the aircraft when in use. And thirdly, the gearbox section transfers the power from the main shaft to an oil-cooled generator that supplies electrical power to the whole aircraft. The general components of the APU usually consist of the bleed air valve, bleed air manifold, oil filter, oil tank, oil filler, APU fuel line, fuel nozzle, low pressure fuel filter, generator, upper stroke, light switch, start motor, exhaust muffler, and the compressor. The APU consists of several components for it to start up properly and to power up the whole aircraft. Different aircraft uses different models of APU, which depends on the own aircraft need. Different models of APU also contain slightly different components inside it. For example, the Airbus 380 uses two each 750 kW generators and load compressors. For the majority of aircraft with APU installed on it, air is used to start the main engines. This air can come from either the bleed air section or the APU, which is just downstream of the compressor. or from a load of compressor attached to the front of the APU. Either bleed air or low compressed air is sent to the main engine and used to turn an air turbine starter, not direct injection to the turbine section. The air turbine starter, like any other starter, it drives a gear train to spool out the main. The other type of APU uses a generator to supply electricity for main engine start. In this case, the starter is an accessory drive motor or a generator that spools out the main to start and then generates power after reaching M1 lights off. More modern engines are becoming only electric machines. These APUs and main engine transformer rectifier units produces 400 Hz of auto current power so that smaller conductors are routed throughout the AC instead of insulated stainless ducts which are very heavy.
Latest research and development of auxiliary power unit. The future of APU on aircraft spells one clear name: fuel cell technology. With recent developments in fuel cell technology, the cost of incorporating fuel cells into a hybrid APU is greatly reduced. Combined with an ever-rising oil price, major aircraft manufacturers such as Boeing and Airbus are taking a serious look into the possibility of having a new generation of fuel cell auxiliary power unit, or APPII APU, to power their future fleet of aircraft. To begin our discussion on APPII APUs, we shall first take a look at what a fuel cell is and its working principles. A fuel cell is essentially a device which converts chemical energy directly into electrical energy via chemical reaction with an oxidizing agent such as oxygen. During operation, the hydrogen in the fuel cell will react with oxygen to produce electricity, and the waste product from this reaction is just water. As long as hydrogen and oxygen are being supplied to it, the fuel cell will be able to generate electricity continually. Two main advantages of the APPII APU are the reduction in fuel consumption and nitrous oxide, carbon dioxide emission. Traditional turbine power APU is used to provide power for engine startup while the aircraft is on ground. APPII APU, on the other hand, can be used to supply electrical power both while the plane is on ground and in flight efficiently. This is because the APPII APU has higher fuel efficiency for generating electricity as compared to traditional turbine APU and the aircraft's turbofan engine. Current turbine APU and turbofan engine have a Jet A fuel to electrical energy efficiency of around 15% and 40 to 45%. Proposed APPII APU has a Jet A fuel to electrical energy efficiency of around 60 to 75%. However, current APPII APU technology is not without its hurdles. At the moment, the main concerns with APPII APU technology are its cost and weight and size. As APPII APU is a relatively new technology, conventional turbine APU is still more affordable for airlines to adopt. APPII APUs are still currently both bigger and heavier than traditional turbine APU of equal output. In order to achieve wide acceptance of this young technology, the APPII APU needs to be more affordable as well as to support higher power density. But with more resources and focus being placed into the field of fuel cell research and development, it is only a matter of time before we overcome these challenges.
Is it a good idea to replace the gas turbine auxiliary power unit with the fuel cell auxiliary power unit? Personally, I think it's a good idea to replace the current gas turbine auxiliary power unit with the newer technology fuel cell auxiliary power unit because the benefits clearly outweigh the disadvantages of having it. Firstly, it's an extremely clean and quiet process, and without any combustion, as the fuel cells only emit pure water and warm air as exhaust, and thus carbon dioxide emissions will be lower as compared to the gas turbine auxiliary power unit. It is also highly efficient and inherent because it has no moving parts, thus no machine cause reliability loss. Its turbo machinery also pressurizes the fuel cell stack, which adds to the efficiency at high altitude flight. The fuel cell auxiliary power unit is 75% efficient in converting jet fuel into electrical power during cruise. Thus is a money maker when it comes to long cruise flights, as it saves a lot of fuel. Finally, in the future, fuel cell auxiliary power units can power airplanes' cabin pressurization, environmental control system, lighting, cockpit instrumentation, wing anti-icing protection, and control surface and landing gear actuation, which frees up all engines and allows them to devote all the power to thrusting the airplane, which is an admirable advantage. Is it okay to turn auxiliary power unit on in flight? Yes, in my opinion, it's a good option to turn the auxiliary power unit on during flight. The auxiliary power unit may be able to power the extra accessories to make the cabin crew more comfortable during flight, or even the hydraulic equipment, which includes slats and flaps, which allows the engine to rest, or substitute the power elsewhere where it is more needed. This way, the engine power is saved and less likely to fail, thus reducing the chances even before it hits maximum power. Using the electric green taxi system to taxi instead of the main engine. I personally think it's a good idea to use the green taxi system to taxi the aircraft. Taxiing takes up to 4% of the engine's total fuel consumption. The green taxi system uses power from the auxiliary power unit to power electric motors that will be in the wheels for the aircraft to taxi. The engine is thus less likely to run out of fuel, as more fuel will be available for the aircraft. This will save money, fuel, and lower carbon emissions, as one small engine will be using lesser fuel to taxi as compared to two big engines which will use more fuel to taxi.